Okay, so let's resume. Let me give a quick recap of the first part. So we looked a little bit at the hardware trends and the emerging technology and the properties of that technology. And the main takeaway was we have to somehow deal with all of the problems that are currently addressed by restarting, because restarting will not clear up the contents of persistent memory, and so we need to think about that. So I'm going to talk a little bit about the other problem, nightmare number 2, which is program evolution for a while, and then we'll get back to how we might think about these problems in the context of programming languages. And really all I'm going to do in this section is kind of map out some choices and talk about the issues and the pros and cons of various choices. And then we'll look at a specific example or two of a set of choices that have been made in a context, one in a reasonably, strangely enough, a reasonably mature system by now that's been around for a while, and then some thoughts about how we might do this stuff in Java. So before I dive in, are there any questions arising from the last section or sort of general thoughts or anything at all? No, okay. All right, so one of the other reasons we restart is because our programs change. And when we change, often accompanying that change is a change in the structure of the data that we're computing on. And so right now what we do is we rebuild our data structures from the copy out in the file system or block storage or wherever we've kept our canonical copy. But if we want to do that in the context of a persistent memory, and we don't want to have a second external copy of the data, then we need to be able to figure out how to do that for memory structures. And databases call that schema evolution. They have a solution to all of their things, but of course languages, generally speaking, don't have any kind of conceptual framework for this at all. Most languages think of, a program as a thing in and of itself. It's not a thing in time, it's just a thing. And all of the data that program operate on are created and managed within the execution of the program. There are a few exceptions to that. Typically interactive systems from the Lisp heritage tend to have ways of saving the working state and restoring it when you start. So Smalltalk is a good example of how to restore stuff. So there are at least some possibilities there, and hence, in Smalltalk you program by just kind of banging on stuff while you're working in an image. And so it has to have ways of changing your program, but many languages just don't have a concept of that. There is an alternate path that we could hypothesize, but I'm not sure I can think of any really good examples of it in the persistent space, which is doing all the changes at the binary level, basically installing patches and modifying our data that way. There is an interesting example actually from Oracle called ksplice, which patches Linux kernels. That's what the K stands for, while they're running. And so there's been some work in this area, dynamic software update, but just quick show of hands, who regularly modifies running programs here and evolves? If you live in Smalltalk, you do. Is there anyone else who does that on a regular basis? No, it's not a common thing. Not a common thing. So what are the challenges of transforming data as code evolves? You have on the top you have some data, and on the bottom you have code. You're transforming in a step from some version to a version n+1. So we need to transform the data from n to n+1, and hence we have to provide some kind of a function that maps our existing data to our new data structure, and it will presumably run in our new version. That transformation could be eager, we do it all at once, or it could be lazy, we do it as we use old pieces. Lazy has the advantage that it doesn't induce a long pause in a big data set, and remember the whole point of this was to have short pauses for restarts, not long pauses. So what are the challenges of doing something like that? Well, you have to preserve somehow all of the relationships in the original data set that were important. You know, things like equality and identity, and your sharing relationships have to be preserved. So if two variables refer to the same object before and the object is updated, you'd like probably those variables to refer to the same modified object. So even if the variables are on the stack in other objects and globals, etc. When you write this transformer, what are the types and the values available? You know, you're writing a piece of code that deals with two sets of types now, the type before and the type after, because it's a function from type to type. These types probably have the same name in the program, so how are we going to name them? You can't just use the name that was in the first version and the name that was in, because it's the same name. Similarly, for all of the values, you have to refer to the old values in computing the new values. While you're computing, do you have access to all of the data that was in the old version? Do you have access to some of the data in the new version? How is the ordering done? Do you have to manage all of that? Those are all questions that have to be answered in the design and managed by the programmer who's writing the transformation. So the typical approach in things like Smalltalk and some of the former literature is to provide default values for new variables and then just kind of let the programmer ad hoc specify all of the stuff that isn't valid by default. So for example, if you add a field to a class, all the instances that exist, you know, get that field initialized to null or 0 or some other default value, and then you have to provide a function that fills it if that isn't the right thing for you, and it's kind of somewhat ad hoc. To do that, you have to sometimes talk about all of the existing values. So imagine that you have a variable that is the sum of the elements of an array, and you've changed the structure of the array, or maybe you've changed it from an array of ints to an array of floating point numbers. Well, now that sum needs to be recomputed. Imagine something now that computes the same thing across a set of objects. Now you have to somehow find all of those things, you know, and maybe those things were not indexed in a way in the original program to do that in a straightforward manner. Maybe that value was maintained incrementally. So a common thing deriving particularly from the Smalltalk world is that you add primitives into the language, which are available during this update, that say, find me all values of this type in the heap, or find me all instances of this class, or find all the references to this particular object. And those are things you have to add into your runtime system. And then once you've done that, if you want to maintain sharing relationships, the Smalltalk approach anyway is to provide a primitive that says, well, replace all references to this thing A with references to the new thing B. So kind of atomically you switch in the new object, and everybody who was pointing to the old object points to the new object. Now that's doable. There is, you know, an existence proof that it's doable, but it has costs. There's a price to pay in the way that you represent things. The operation itself is not cheap because in principle you're scanning the entire heap, finding those references, and if the heap is a petabyte, that, you know, there goes your small pause. It becomes a long pause. So there's a whole bunch of interesting issues here, and not a heck of a lot of work. I mean, if you wanted to list all of the literature here on this topic, you know, it's the kind of thing you could read in a month, probably, maybe 2 months. 20, 30 papers, probably not even that. I can only think off the top of my head of maybe 10 or 15. It's just not a lot. And so this is somewhere where there's a requirement. We need to be able to evolve this data if we're going to use persistent memory without recomputing it or storing it in a file form. And so a need, but no real solution that's been widely adopted, tested, used in practice. Most of these things, the existing literature have either been used to evolve data as the programmer is doing development work, and so the data are development data, not deployed data in production, or it's being used in the context of debugging, you know, fix and continue debugging. Java has some facilities to do this. You probably never heard of them. They're very, very obscure, and they're used in fix and continue debuggers. But it's not complete. You can't do everything that you need to do this. So there's more work definitely needed here. And even once the basic mechanisms are figured out, you know, we have to figure out the methodology and train people to use it correctly, because it's persistent data. If you get this wrong, you mess up in a big way. Okay, so we got these two big problems to address. But before that, we have to decide how persistent data are described in a particular programming language. So we need to make some design decisions if we're going to add persistence to a language. And so the next section is really running through some of those issues. Any questions, comments to this point? Okay. All right, so the main requirement, the most challenging one, is that we need consistent states, because when we recover after a restart, in particular an abnormal restart, one that was caused by an external event or a bug, we have to go back to a known good state. And so we have to know what the good states are, and we have to be able to recover them from the actual state of the heap. So there's two different things there. So what, the typical kind of solution here is taking, in effect, logically snapshots from time to time and logging the important events that connect those snapshots. So that when there's a failure, we can recover to the previous snapshot and then apply the log to compute forward, or if it's an undo log, start with a snapshot and go backward, you know, the current heap, and go backwards to a point that's consistent. What kinds of things are we going to have to do? Well, imagine we have the case where we've had abnormal termination, and we have a chunk of persistent memory that was attached to a running process before. Now, if that abnormal termination was externally caused, so it was because the power failed, or the operator hit Control-C at the wrong time, or something like that, then generally speaking, just before the termination, everything was going fine, right? The moment before the signal arrived, or the moment before the power went out, it was doing exactly what it was supposed to be doing. And so we don't need to go very far back, because things were good. We potentially have to unwind only a short period, because there was no fault. Now that's a little bit, I'm lying a little bit, because one of the reasons we can get external abnormal termination is the persistent memory system says, that block, sorry, ECC is wrong, and that particular chunk of memory now is gone. But ignoring that one, generally speaking, we don't have to go back very, very far. However, if the problem was caused by the typical scenario, which is data became inconsistent, corrupt, whatever word you want to choose, and was in a bad state, then life is trickier. So the case where your laptop application is behaving weirdly and you can't figure out what's going on, and so you terminate it and restart it, well, clearly recovering to the exact state it had before you restarted it really isn't that helpful, because you'll be in exactly the same broken state. You need to get back to the last good state that was there, and that in general is tricky. So that's that description. Sorry, I think I had... this to me gives us a hint as to why the separation of state into memory and files works, right? We restart and the restarts work, and generally speaking, when we restart, we don't lose stuff. Why is that? It's because the storage operations are usually correct, and the memory structures are not. And the reason that is the case is because the storage operations are often in a structure that's simpler, or well documented, or better tested, or whatever. And so perhaps this is the hint of how to manage this, that we have to partition our data into the stuff we really care about and the stuff that we can throw away at a restart. So maybe one strategy here is to treat file storage as the core stuff that we care about. And then memory is really two things. One is cached values of that we have more efficient structures to access and do the computation that we want. And the other part of memory is effectively a scratch pad, the in-progress calculations, data, etc., that are being used to figure out an update. So we've got a distinction into three things. The stuff we really want to keep, the stuff that's there as an accelerator, and if we break, we can throw it away and recompute, and the stuff that's just transient that we don't need at all when we restart. Yes?
My question is though, don't all operating systems do that with hibernating? Save save the important stuff on the state, and when you reboot, reinitialize the hardware, for instance, and then go back to the...
But hibernation is a scheduled event. You close the lid, or you decide to put the thing to sleep, and on the assumption that it was good. Right? If it hibernated because there was a bug, when you opened it, the bug would still be there.
I mean, that's also true with faulty firmware that does, ungodly stuff with UEFI variables, and then the machine gets bricked, like some Samsung laptops with the kernels.
But there's even more. When you hibernate, you actually the OS, you say to the OS, please hibernate. It says, okay, each device driver, please do whatever work you'd like to in order to hibernate. So it's actually got a chance to be worked on.
Right.
It takes a couple of seconds at least.
Right.
So it's not, you don't...
Get one of those systems and pull the power out of the wall and see how well it's hibernated. Okay, so there's a distinction here in practice that we don't, it's not reflected in our language, right? It's not reflected in our programming languages, not reflected even in, other than the way we think about the data. We think only about, it's kind of implicit. The files are the important stuff. The stuff in memory is not important. We can lose the stuff in memory and we keep the stuff in files. And so if we're moving the stuff in files into memory, we should really maintain this distinction somehow.
Now, this is sort of what Intel proposed with their diagram, right? Where you have maybe a part of the memory that you access sort of like the file system, and then you have a part of the memory that you...
So if you're willing to keep the data that you care about in files and pay the price of accessing those through the file APIs, then no problem. You just leave the program as it is and you just move the files into the persistent memory. But the dream here, remember, is to eliminate the second representation. Because in that representation, you have the files in memory and you have the data structures, which are a copy of the files read into data structures in memory. So it's all in memory. And you've got the duplication, the code to maintain both representations. So if the goal is to do away with one of those representations, we have to do that, but still be able to isolate the data structures that we want to keep in the case when we restart and throw stuff away and figure out what stuff we're going to throw away. So we'll get back to this a little bit later. Yeah?
So I haven't thought this through, so it might turn out to be wrong, but just as an idea, isn't this spiritually similar to multi-core data structure design?
Spiritually similar. You're going to have to say a little bit more.
So the comparisons I'm making are these sort of good persistent stuff is what all the cores can see. And then you have other miscellaneous structure-specific things that are either scratch pad or cache stuff, which may be interrupted if using hardware transactional memory, or your thread might crash or something like that. So
yeah, maybe. I'm not saying that this has never been thought of or done before. It's just that now we have to make this very, very explicit, I believe.
just kind of
Okay, so we need yes.
Do databases already have to ask similar questions about their in-memory versus on system?
So databases, because, and we'll get to databases in a little second, but because they've already basically addressed this problem. But one of the ways that they do that is that they push the problem to the clients of the database and say, you better tell me when you're done with a transaction and your update is done, right? You have to, there's a notion of that in the interface to the system of which things are consistent and which things are not. And so we have to recover this, you know, ultimately when you go further and further back, something has to decide that.
So I think what you're saying is this, philosophically, is that our current situation when you've got RAM and hard disk or whatever, is that there are implicit like commit points. And if you shove something onto the disk, you implicitly.
Yes. Yes. Yes, that's right.
This is going to get harder. I mean, like, imagine I have 100 levels of storage and stuff. That would be hard to get right. So when does it get harder? Is it 2 levels, 3 levels?
I think in all cases it's going to get harder in some sense. But there are benefits that would make why we would want to do it, and those are around the latencies and the capacities and the economics of non-volatile memory. So it's kind of it's a bargain where you accept the risks and the complexity in exchange for some benefits. And the other benefit might be that you don't have to write the file code. If you can get it right in the data structure and do the separation, well then you haven't got a file anymore. So what is it that we specify when we specify consistent points? There's a big range of possibilities here. We could have transactions and operations that are maintain consistency of individual small data structures and then compose the consistency of the system out of the consistency of the components, or we could just say, it's the entire program state and we're going to pick points where we believe that's consistent. And both of those, they both have advantages and disadvantages. The sort of the CS compositional scalable person in us all says, oh, it should all be small, we should use composition, etc. But that's a big, it's a big burden to specify that for every single data structure. Whereas in some cases, at least, for some applications, just saying, okay, I know it's consistent now. I'm talking to one user, the flight has been booked, all is good. So there's a scale issue that has to be decided. So databases, of course, have done this and have dealt with this. And the typical way is there is some notion of a state that is a known consistent state that's identified by the client of the databases. This is the point at which I'm done with my update. The system then implements an update, and during the update it's inconsistent, and then at the end of that either we commit and save a new consistent state, or we abort and roll back to a previous one. And in early databases, this was commit was a global thing, right? Every transaction ran in effect serially, and there was no requirement to state what you were committing. It's like, whatever the state is now, I'm done, it's committed. And it's actually a very easy model for people to understand. It took a long time, and mainly the demand to get more performance and scalability to try and do transactions concurrently and deal with more restricted notions of consistency. The other thing worth noting is that the overall control of the system is in the hands of the client programs. They are driving the inputs and the outputs. They're external to the database. And so non-volatility of the database is good, but we want non-volatility of entire applications. And so the notion that there is something outside that is driving this isn't helpful here. We need to be self-contained. We need to be able to have consistent single programs that aren't being driven by externally defined transactions. The unrolling has to end somewhere. So databases implement this ACID notion? Who knows what the acronym stands for? What's the A? Atomicity, right. So atomicity is the notion that each transaction executes all or nothing. That if there's a failure, we're either in the state after the transaction or the state before. And we sure need that if we're going to do this. That's clearly a given. So this, I put it up for you. C is consistency, but I think you probably could have guessed that from the slide, and I don't think anybody's going to dispute that that's also a requirement. What's the I? Anyone? No. No. The I is the one no one remembers. It's isolation. The notion that transactions execute as if serialized. The state of one transaction is the things you see are as if you took a snapshot at the beginning of the transaction. You run the transaction as if nothing else was executing concurrently. And when it commits, then that state is logically the state of some other transaction. And what the databases actually do is they give you this illusion, meanwhile juggling all of the balls underneath, that say actually these things are running concurrently, and if they conflict in some way, if one of them reads something that the other one has written, there's an abort and a retry. There's a vast amount of machinery to implement this, and it's not what we do when we write programs in concurrent programming languages, right? You don't write variable updates as if there were things going on in the in a serialized transaction manner, except if you do actual, transactional programming in the hardware, which is, usually tiny little updates. So this one, I think, is up for grabs. It's not clear to me that programming languages need to provide this because, at least in some programming languages, I think the programmers will want to manage their own concurrency rather than have it automated for them and pay the price of that automation. The D? Durable. Well, that's kind of the whole point of that talk. So yeah, we need that too. Okay. So again, in the database case, there's an external program, and the external program talks not only about transactions starting and committing, but it also has logic to decide on aborts and what to do when there's an abort. So there's a controller that's outside of the domain of the non-volatile world that's prodding and seeing what's going on. But in a program, if you imagine writing a language in which the transactions were all in memory operating on the same thing, if you did an abort and there was literally the abort rolled everything back to the state that was there at the beginning of the transaction, you just do the same thing over and over again, right? You need something to tell you aborted, some element of state that says it's not the same as it was when we started this transaction. So there's an interesting question here as to whether that logic is something that's expressed as a first-class thing that programs can talk about, or whether it's just an implicit kind of thing that's there but isn't a language construct. So for example, if your program aborts, maybe you just quit if your transaction aborts, maybe you just quit the program and you have to restart the program, but it's rolled back to the point at which the last consistent state applied. So there's in that scenario, you don't have necessarily any way of talking about the abort logic. You only have a choice of whether to commit or abort. And let's go down a level. We need now also to think about how we specify that persistence is done. Which data in our heap or our program are actually persistent? Is it everything? Probably not, because persistent memory, as you've seen, is slower than DRAM, and so I think very few enterprise applications are going to want to just put everything in persistent memory. There's probably going to be a difference. Now, is that difference something that's manifested at the programming language level, or is it managed by the runtime? So that's one immediate distinction. If it is manifest at the programming language level, how is it manifest? And here are some choices. We could specify by type which things are persistent. So, a particular type could have a persistent keyword or an attribute, and all instances of that type would be persistent, and other types would not be. we could specify per object, say when we allocate it. When we make an object, this object that's just about to be created is a persistent object, put it in persistent memory, and if we don't say that, it's put in volatile memory. Or we could make maybe that decision dynamically. Okay, I have an object, it's volatile, but now I want it to be persistent. Please, do whatever it takes to make that happen. Or another option is by reachability. So this is a case where it's in effect implicit, mostly, except for the specification of the roots of the reachability. So let's look at each of these in a little bit more detail. So types are initially attractive, but there's a problem, which is that often we want instances of some types to work the same whether they're in volatile memory and in persistent memory. And so our type system either has to admit that as a possibility, that we can take a thing and use it in both contexts, or it means that we're going to end up with some code duplication because we've got, we need different types for the different users. One interesting question here is, legacy code. Most all languages existed before the advent of persistent memory. Can we take existing code and interpret it in some way that we can use it in a persistent context without rewriting it? Or do we have to rewrite everything? There's a particularly interesting problem with static types. Generally speaking, static type systems assume that the program is type checked before the data are created. So you run a program, you run a type checker, it says, okie dokie, this is all good. And then you run the program and stuff appears. That's not going to work in this system because the stuff existed before the program was type checked, or the program could change and the types could be checked. So one of the challenges in a statically typed language is to have some way of, in effect, type checking the program against an existing heap to know that those are somehow consistent. Do they have to be exactly the same types? Can they be a little bit different? What difference is allowed? What differences are not? When it comes to the actual compilation, then it's really good if our compiler knows when we're talking about something that's persistent versus something that's volatile, because at least in the Intel system, there are extra instructions that need to be omitted in the persistent case to flush the caches and stuff like that. We could put those in the volatile case too, but they're all fairly painful in terms of the performance, and so we'd like to omit those if we can. So either the system has to figure out that that's going on and omit those instructions, or it has, potentially, it has to be told when persistence is happening so that it can generate the code. There's also this issue that I mentioned last time of lifetime correctness, right? We don't want persistent data to reference volatile data. And if we want to make that into a checked error, we either have to design our type system to ensure it, maybe there's some funky version of ownership types that would give us something like this, or we have to make the runtime enforce this. And then as the program is running, because we have some kind of a transaction in process and some notion of a consistent state, every time we generate updates to that, we need to generate some kind of metadata to be able to recover back to that original state in the event of a failure. So for example, if you have an undo log, updates to variables in persistent memory have to maintain that undo log, and you'd rather not have to have the programmer do that explicitly. That's what compilers and languages are for. I mentioned persistence by reachability. So this is a kind of an attractive option on the face of it. So the idea of persistence by reachability is that we designate certain variables or values as being persistent roots. So those, let's say we choose some objects to be persistent roots. And once we've said that in our code explicitly, those things are placed in persistent memory, and anything that's reachable from those things are also placed in persistent memory. And one of the benefits here is that if you want to take some existing code and make it run in this world, then really all you have to do is sprinkle in the persistent routes, and the system takes care of everything else. And that looks very, very attractive, at least initially. So the distinction between persistent and volatile is minimal, really, in the changes to the code, and the runtime is doing everything for you. But there are some properties which at least make me a little bit hesitant to adopt this. I'm not saying this is absolutely the right answer. This is one of the things that's up for discussion, and I think there will be systems built that try both approaches to see which one is actually more usable in practice. But one of the problems with persistence by reachability is that a single reference assignment can result in kind of arbitrary amounts of data suddenly becoming persistent that were volatile, and in principle, arbitrary amounts of persistent stuff really being volatile because they're not reachable from the persistent routes. Now, the former of those is the harder problem, because the implication, I think, is that the transaction you're in has to have all of that stuff actually migrate from volatile memory to persistent memory before it completes, and that could be a very long period of time. And it's a property that's non-local, right? When you write an assignment, unless you know the structure of the thing you're referring to and everything it refers to, etc., you really don't know how much stuff that's going to be. In the other case, when you snip the reference to something that's currently persistent, what you'd like is for that to become volatile eventually, but that's a property that, the system can sort of do that in the background to save the memory without you being aware of it. So the former of these is a little bit worrying. The other, I think, bigger problem is how to avoid entangling what I called in the earlier slide the core state, the stuff that you really care about, with the stuff that's the caches and the other computations and the scratch pads. A single misdirected reference here connects things, and so when eventually you have a bug that requires a restart, how do you disentangle the stuff that you really care about from the stuff that you don't care about? Yes?
Just to double check, you're talking about dynamic reachability. This is all done based on
Absolutely, dynamic reachability. So exactly the same as garbage collection. Exactly the same. And in fact, well, I'll talk about this a little bit more. The typical implementations here sort of piggyback on top of the garbage collector. So then we have a bunch of practical problems in implementation which we have to address. So for example, if we have a garbage collector and a garbage collected system, the garbage collector itself has to be, in its operations on the persistent heap, has to be resilient to failure, because the interruption, the restart, could happen while the garbage collector is running. We could probably work on the assumption that the garbage collector is correct, because that's a hard one to deal with in general. If it's not correct, to recover to earlier versions in a sound way, and the GC will presumably have a lot of it. Maybe it'll be a validated garbage collector, and then we'll be happy with it. But there are some technical challenges in making that actually work. We might have in our address space in the application that's running some unmanaged code. Random stuff that got linked in that we don't have the source to. It might be in an unsafe language, and be able to, if that has a bug, which surprisingly even commercially acquired software has bugs too, and it stomps on some of your persistent heap, all the types in the world aren't going to protect you in your code. If that random bit of code in the address space stomps on your data, it's gone. And so we need to deal with that situation. Let's think about managed runtimes. When you run, say, a Java virtual machine, then the objects and the object representations underneath that virtual machine are the choices that were made in those decisions were the exclusive province of the VM implementer. And when you get a new version of the same VM, those choices may be different. because the data are volatile and currently. So the layout of objects can change from version to version. The layout of objects between different versions of the JVM from different vendors are probably going to be different. If we now assume that we're going to get heaps that last for 10, 20, 30 years, how are we going to manage this layout? We need to have some kind of stability in the system. We need to have some way of transitioning and evolving over time and maybe switching versions and switching implementations that allows us to do this. Now, this isn't really a technical problem. This is a social problem, right? We need to get vendors to agree on stuff, to document stuff, there are standard organizations that probably need to get involved, etc. But there's a bunch of stuff that has to be done to make this actually happen, because otherwise, you'll end up in the state that some number of years pass, the vendor changes the VM or goes out of business, and suddenly your persistent data are useless because you can't get a new VM to do stuff. Do you have a single monolithic persistent heap in your application? Or do you have a partitioned modular thing which requires at least something in the code to distinguish between those two? And then there's this ugly wart of objects which defy persistence. So if an object refers to some external state, then if the external state changes independently, then the object doesn't reflect the change, then it might not work anymore. So let me give you some examples. So if you have an object representing an open file, and that object uses, say, a file descriptor or a path name, and you suspend your program and you put this object in a persistent heap, when the thing comes back again, the file may have gone. Right? The descriptor could have closed. The path name may no longer be valid. So at resumption time, at that point onwards, things are not going to work. Here's another example. Suppose you have captured the process ID of the process that you're in as an int inside your program. A thing that happens all the time, say in a Unix system, because that number is used in the creation of temporary files. When you resume that program, process ID is going to be different. And if there isn't some code to manage that change, to find that int and update it, and everything that depends on that int, it's going to be wrong. Or imagine taking your program that you ran and a heap that you created while you were in Italy with an Italian locale, and you take that heap and you go somewhere else and you change the locale and you run the program again. Where is that locale being bound into the code and the data of your program? That stuff has to be caught and updated. Yes?
So what your title is underplaying. It's not, the worst thing is the objects don't define persistence, they're persistent, but they undermine guarantees.
Exactly. Imagine the case where you have a stack and you've called out to some external code, and on your stack are references to that code and frames and variables, and that stuff was all in volatile memory. Well, you're not going to reconnect that after you've started. So there are all these issues, and we're either going to have to find out ways of finding these things and flagging them when we restart and reuse these objects and going, this is broken, or better still, would be requiring that the programmer specify how these things get reconnected or the error handled when the program resumes. So we have a phase in program data management, which is the resumption moment, when things which are in the persistent heap that require references to external state, they either have to be reconnected or an error has to be thrown and the error handled in some way, or we just have to say no to putting any of these things in the persistent heap. But it's kind of tricky if you have to ban all ints. Yes?
So I don't need the PID. Well, I calculate a temporary file name for my PID. So now, unless you capture the information, well, I get to the sound type.
Yes, exactly. Yeah. So all that stuff has to be somehow captured in the program. that has to be a dependence on some datum that's recorded as being a volatile thing, even though it's been persisted, and either recomputed or discarded. Okay, so I've listed a whole laundry list of issues. Let's look briefly at a couple of different approaches that pick different points in this space. So my colleague at Oracle, Bill Bridge, has been thinking about non-volatile memory for some years and has come up with an extension of C for persistence called NVM Direct. And there's a free version of this available on GitHub. So in this approach, we have an explicit separation of volatile memory from persistent memory. There are persistent regions and the rest of the heap or the rest of the data are volatile. And then a notion of transactions which operate on some subpart of each of one of those persistent regions. So when you write a transaction, you can have multiple regions that come from either different parts of a persistent file or from different persistent files, but when you operate in a transaction, you specify a particular region that you're making changes to, and you're only allowed to change things in that region. And associated with a transaction, you have locks available that you can take, and compensation code which is run to deal with transaction failure. So this compensation code might undo things that have been done since the last consistent state, or attempt to complete in-flight transactions or whatever. There's a whole literature around this. Then to distinguish between the actual persistent data and the volatile data, there are syntactic extensions to C in this language. So when you declare a pointer type to a persistent object, you use a different notation for that. When you write an assignment to a persistent variable, you use a different notation for that. So the syntax that you can use to figure out exactly whether you're talking about volatile memory or persistent memory, and the compiler can then use that to generate the flushes and the undo records and all of that stuff. But it does mean that an existing piece of C code is all volatile by definition, because it doesn't use any of the syntax, right? You have to add all of this stuff in. So let's have a quick look. Oh, and as I mentioned earlier, you have to have position independence, and in this case, the compiler manages that by using self-relative pointers for all persistent data. So here's a fragment of code from one of Bill's examples, and you can see it sort of looks like, it's recognizably C, but there's also parts which are new. So there's the persistent keyword on the definitions of types. There are types introduced by the library, things like the non-volatile memory mutex, which is a mutex that lives in persistent state. And then here is the syntax for a transaction, which says we're going to start a transaction. We're running the transaction on the region of memory that's labeled by this region descriptor. We can access locks associated with that. And you notice the dereference operator looks different, and the assignment operator, I'm not sure I've got an assignment operator here, would look different. There's syntactic differences that indicate that you're in non-volatile memory, and the compiler checks that you're doing the right, using the syntax in the right place. Yes?
Since the syntax only for pointers, I assume that the stack is always non-persistent.
The stack is volatile always. Threads cannot be persisted in this model.
So you can't resume to a previous point of the program, actually. You can only restart the program.
You restart the program, and so one of the things you do here is that you record with each transaction. You can do things like record abort actions or recovery actions, and the locks are persistent, so when the recovery begins, you hold the same locks that you had on the transactions, and the actual transaction objects are persistent. And then what you have to do is run the recovery code that was specified with that transaction to get you back to the state that you expected. In this system, to handle the software evolution problem, basically the programmer has to figure out when changes are significant for the structure of the heap. So C programmers generally know about how the types map to some kind of a layout, and this kind of piggybacks off that. So for each particular version of a data structure, there's a unique version ID, which is just some long bit string. And that is stored with the structure and with the code, and if those match, everything is good. If they don't match, then either a piece of code has to be supplied that says, okay, I know how to deal with that old version, I'm going to convert it when I restart, or it's just an error and the update is, the program is not allowed to run any further. And the IDs are basically constants declared on types and files, and the programmer has to explicitly specify when that thing changes. So if you make a simple bug fix that doesn't change the layout in any significant manner, you can keep the old version and everything is great. And if you make a change that is going to break your system, then you need to change the ID and supply some transformation code. So the burden of management is on the programmer, but this kind of thing is being used internally at Oracle to build things like databases, and those programmers are expected to carry a heavy burden. So, c'est la vie. Any questions about that? Okay. So let's spend the rest of the time looking at Java, because this has been the focus of what I've been doing, so about half an hour. So Java is very widely used. There's lots of programmers and lots of code. And my goal, at least, in this work is to try and figure out a solution that would enable lots of code reuse and lots of mental reuse to occur, i.e. you don't have to retrain all the programmers that have to use it, right? It's recognizably, familiarly Java with some extensions, and the extensions are not massive. And that's kind of the central point. There are some existing approaches in the literature which I've considered, and I'll tell you why I've rejected these. So Intel, along with its release of Optane, has released a library called Persistent Collections for Java that you can get from their, it's actually on GitHub. And this library, it works on all VMs. It's not a new VM, it's a standard VM which connects to persistent memory through JNI. And so the persistent data are actually not in the Java heap at all. They're actually off in the C heap that underlies this system. And what they do in this system is they basically construct proxy objects at the Java level which stand for the persistent data and forward the appropriate operations, the updates and the reads to the underlying persistent data. There are a couple of issues with that. One is that there's an awful lot of extra memory needed for both the proxy and the original copy. So that's a little bit of a concern. But perhaps the biggest thing that I find problematic with this approach is that they use a separate parallel type hierarchy. So they introduce P object as a subclass of object, and everything that's persistent has to be a subclass of P object, which means everything in the Java libraries that exist, none of that is persistent, end of story. Everything has to be created under this new type from scratch. And when you do that, you end up with just a lot of kind of duplicate stuff, because if you want something to work both ways, well, you can't. You have to have a thing that sits in front of that manages the distinction, etc. It just doesn't feel like the right answer to me. I understand why they did it, and it's perfectly reasonable as what they describe it as, which is an experimental library to get people playing with persistent memory using Java, but I don't think it's a particularly good long-term solution. And if I showed you some examples, you'd probably have the same horrified reaction I had. So, but I'm not going there. This is not a rant. Okay, so there's another paper. Yes?
If you take an existing Java project, like something from the standard library,
yes.
The subclasses with global inheritance with P and this object.
In this?
Yeah, all the things coming from the standard library is still non-persistent, but everything you introduce in the subclass is persistent.
So I think what you're asking is you can have interfaces that you introduce that don't really affect the decision of whether you're persistent or not, but anything that you want to be in persistent memory has to have its class inheritance trail back to P object.
Yeah, but you can have multiple inheritance in Java. So if you have some, let's say,
no, I don't think so. Yeah.
Okay.
Yeah, okay. So there's a paper, maybe a couple of papers that describe a research system that's called Espresso, and they take the approach of adding a new operator. So there's pnew, which is analogous to new, and pnew allocates in the persistent heap. This is an interesting approach. It's, sort of persistence by reachability after that. But the problem here is that, well, there are no pnews in existing code, and so kind of adopting this model and not throwing everything away is kind of a little bit problematic. There's a more, I think, plausible piece of work that's come out of Illinois called AutoPersist. I have 3 papers, and I'm citing the most recent one, which has been accepted for this year's PLDI. And in this takes kind of the reachability approach and follows it through. So they split the heap into persistent and volatile parts, but that's transparent to the programmer. The programmer just labels some statics with a special annotation and says, this is now durable, right? Everything reachable from here has to persist. And the implementation underneath checks when you store a reference to a volatile object and a persistent object, and so extend the reachability, copies all of the stuff across, installs forwarding pointers, lots of GC hackery, hilarity ensues, and eventually, you have all of your stuff in the persistent heap and the forwarders in the old heap, and at the next GC cycle, it cleans up the forwarders and all is good. So it can be done. Well, we kind of knew it could be done, and this is a revisiting of some of the old work to give you persistence by reachability. So on the previous slide I mentioned there was work on persistence and reachability long before we had persistent memory. And this is fairly close in spirit to that approach. And then to get consistency, they add the notion of per thread failure atomic regions. And the VM implements the undo logging so that when the thread gets if the thread gets interrupted by a restart, it winds back to the state. It does unwinds all of the things it wrote to get you back to the earlier thing. But they don't attempt to give you any kind of isolation. Every thread is doing this independently, and each one has its own choice as to where these regions begin to end. So the programmer has to deal with some complexity. But the underlying machinery is all provided. And where's Salim? This is all implemented on top of Maxine. So hooray for Maxine and Ben. Ben, yeah, there you go. You're not asleep. Good. And then there's fun about things like determining when you do a new, should that new go in volatile memory? Because if you make that decision wrong, you're going to have to copy it later and fix up the pointers. So if that particular allocation site tends to make persistent things, why not just put them in persistent memory? And it's all good, clean VM hackery. And I don't mean that in the bad sense. But again, we have this reachability issue, which is this the right way of doing things? Reachability is a non-local property. We have all of these problems around finding reachable data and copying them, and pauses that could induce. And some objects, even in this system, threads cannot be persisted. So even though for a pure Java program, you could probably figure out how to do that with a lot of work, in this system they go, no, you just can't do that. So there's another approach, and this is the one I've been looking at, which is the NVM Direct partitioned heap, the notion that we chop our heap into explicit spaces, some are persistent, some are volatile, and the programmer has to manage those boundaries. The persistent regions are mapped from DAX files. When you allocate in a specific region, and we disallow cross-region references except in the case from volatile to somewhere else. So when main begins, we have a single volatile region, the red thing, And the program can map the green things, which are persistent regions, from DAX files by making API calls. And then as time evolves, pointers get made. Internal pointers are fine. You can always have pointers internally within a region. Pointers from volatile to memory are fine. But if you try and install a pointer going the other way from persistent to volatile, that's an error, and it would be caught by the runtime. And you'd get an exception at that point. So, and similarly, you can't have pointers from one persistent region to another, because those persistent regions are supposed to be independent and could be loaded at different addresses and have different lifetimes. It's external state, so you're not allowed to do that too. Now, rather than go down the path of having a persistent new, which has this problem that there are no persistent news in existing code, and so you can't use any of it, the approach I've taken is to say that every thread has the notion of a current region, which is where it does its allocation. And this current region can be changed by the program, and so you can easily wrap this in some calls to make it ineffectively dynamic. So in this case, what I'm doing, I'm saying, run this lambda using this region as the allocation site for everything run in that thread while it executes. So in this case, we're just using a standard hash map. The hash map gets allocated in the region, et cetera, et cetera, et cetera. And if h is a volatile variable, that's an OK assignment, no problem there. And all of that should just run. Now, what am I using for a consistency model? Here's where I differ from NVM Direct. NVM Direct has the nested transaction compositional model, which, Tony can tell you way more about that stuff than I can. It's all good, it all works, it's great, but it isn't Java as we know it. And so if you try and write programs using that kind of model, you don't really port or reuse existing things. You kind of have to do a lot of rewriting, because it introduces a different way of thinking about the evolution of structures over time. I don't really have the time to get into details, but it doesn't feel to me like a good short-term solution. I think it's an excellent long-term solution, and I don't see any reason why we need only one solution to this problem. I think that we could have multiple coexisting approaches, where you pick the approach depending on what you're trying to optimize for. Is it, time to get the program running? Is it scalability? Is it performance? I don't doubt that there is a single winner that beats everything else on all scales, which means that we probably need different approaches. But I've gone the other direction, which is simple checkpointing of regions under the control of the programmer. So the programmer can invoke a checkpoint primitive on a region, and that logically takes a snapshot of that region at that exact state. And if the system gets restarted before the next checkpoint, the runtime will ensure that when it wakes up, it looks like it was at the point it was checkpointed. And you can choose to checkpoint regions independently or together. Why would you want to do things together? Well, suppose you have an implementation of an in-memory database. Checkpoints are probably going to have some property that says they take longer to do the more you're checkpointing. And so you might want to checkpoint the bulk of the data infrequently, but the log every time you have appended a record onto it, and that would be a lot smaller. So checkpoints in this model basically induce the notion of different epochs on the data that run between the checkpoints. So we have the data going through these series of epochs, and each epoch's boundary is a checkpoint. And so when you take a checkpoint, the state of the region is in effect frozen at that moment. And the data within it become immutable, but we keep any modifications in the successive epochs. So when you modify an object for the first time within a current epoch that you inherited from a previous one, you get a copy in non-volatile memory. You then have your copies, your modifications done there, but your old version is still around for recovery. So I'll show you that in a second. Going the wrong way there. So when a restart occurs, and the epoch is attached, a region is attached, but it was not committed at the time, then the recovery takes place and it unwinds to the previous state, discarding any of the modifications since that last checkpoint. And the locks are associated with threads. Threads are volatile, so the locks are all discarded, and the program has to reestablish all of that stuff. So each checkpoint in this model persists until it's explicitly discarded. It's a bit like time. If people are familiar with Time Machine on the Mac, you have a bunch of ineffective snapshots of state. You can delete one in the middle and things get merged. You can delete the oldest and that's gone. You can't recover to that, but a new one becomes the oldest. It's a fairly simple model to explain. So what does a programmer have to do to convert existing code to use this model? You have to do the partitioning between what lives in DRAM and what lives in NVM. You have to add the logic to create regions and load them and attach them. You have to wrap stuff in the code that sets the allocation region, and then insert checkpoints at the places when the region is consistent. So here's a simple example. This is the notion is just an object containing a hash map. You see the types are just standard Java types. Now we have a new thing called a region, and the region has a root, and the root is typed, so the type of the root is the type of the thing that we want to keep in the persistent region. So regions are parameterized by the type of the root. And then we have a piece of code that says, okay, here's the name of the file out in the external world that contains our region. What we're going to do is try to attach that to this heap and access it. If it doesn't already exist, we're going to create one and initialize the root using this code, which makes a new hash map and installs a reference to it, to the root. And then that can go wrong in a number of ways. Either we mentioned a file that isn't there, or the file is somehow not the right format, or the type of the root is not the right type, and we have to deal with all of those problems exist in our code. And then when we're done with this, we have an attached region that's either just been freshly made with a new hash map, or the old one that we had the last time we ran the program, the last time we checkpointed. So then imagine further down in the code where this is like a simple phone directory. The example is lifted from one of the nested transaction papers. We're going to add an association to the hash map. This is how the code would look in the normal volatile case. And we have to make a little change. We have to wrap our put in region code. And if this is our update, then we have to do the checkpoint explicitly at this point. Anyone see the bug? Okay, clue. The strings were in volatile memory that we passed in. We can't install references to volatile memory from persistence memory. We have to copy them. Yeah, I knew that would be a reaction. So in this case, I make that very explicit. Because strings are immutable, in principle, the runtime could just do this for you, because how would you know that it had been done? But in general, arbitrary data structures, you can't just randomly copy stuff. The program has to be aware that a copy is being made. How do we deal with things that are inherently volatile, those objects which defy persistence? Well, they have to reside in the volatile partition, and they could be annotated to enforce that, or you have to add behavior inherit some interface that basically says this needs to be reconnected when the partition is reattached, and the runtime will arrange to run your reconnection code and deal with whatever you decide at that point, whether it's allowed or not allowed. And you could, in principle, do the same thing to handle inter-region references in the same way by having reconnection code reestablish those. That's always a possibility. A particular twist that intrigues me is the notion of not even making the checkpoints explicit. The exit is the commit. An exit of 0 is a commit. An exit of non-0 is an abort. Imagine the case where your JRE is in non-volatile memory. All your data are in non-volatile memory. You have a pre-initialized copy of the volatile heap that you can grab by copying from non-volatile memory. Startup could be really, really fast. So why worry about having explicit notions of transactional code? You could just have each program be this little small step. I'm taking a heap, I'm going to transform it into another persistent heap, and I'm done. And that's one epoch. It's kind of an interesting model for very simple confined code. Perhaps the serverless world would look plausible in this. Anyway, this is something I'm looking at. So how would you implement this? I'm assuming that regions could be loaded anywhere, and so the data within the region have to be self-relative. We want checkpoints to be fast so they can be used relatively often. We want checkpoints of smaller things to be even faster. And rather than optimizing for crashes and recovery, which are assumed to be infrequent, we optimize for the steady state performance. And we can do some trading of space for time because we just got all this cheap, large memory, so why not use it? So the assumption that this is a sketch of the direction I'm pursuing. The idea is like all computer science problems, you solve them by introducing an indirection. So in each region, logically, we have an object table, which is an indirection. And so in the region, the reference to an object is a reference to its object table entry, which lives at some the object table lives at some well-known place. And then the object table reference is the most recent version, the working copy in the current epoch. And each one of those, so we have a reference to the object table refers to the current version, and each version refers to its predecessor. And so recovery is just a question of going through the object table, finding things that point into the green bit, winding the object table back to point into some blue stuff, and then you can restart. And so you need, obviously, extra space to do this. One of the interesting points of this is if a region is less than 4 gigabytes, the self-relative offsets can be 32 bits. Don't need 64 bits. Because you can't cover more than one region's worth with a pointer. Some additional details. My current scheme has write protection using virtual memory to write protect the older epochs, catch writes, do the copying, patch up pointers. Not super fast, but not super slow either. We need some kind of a barrier check to check for cross-region stores. I don't see any way of removing those ahead of time. The compiler, I think, can optimize a bunch of them away by, the property doesn't change. So if you know the region of the source and you know the region of the destination and the same region, well, once you've proved that, you can assume it for the rest of the life of those references. And in fact, even though I pictured it as a single contiguous thing, it actually has to be chunked with alignment restrictions to get a bunch of things to go fast. So the research questions around this, the most important one is this useful? Which programs is it useful for? Where is it not useful? What kinds of mistakes are people going to make? What's the mitigation for those mistakes? Is the partitioning going to give us the reliability that we're seeking that we might not get from reachability? Maybe reachability is good enough. I don't know. I think we'll find out. This certainly doesn't scale like his stuff does, you know, find transactions and all of that stuff. It isn't going to supply that kind of model, but it doesn't require massive rewrites, just some rewrite. But he's skeptical, so I'm waiting for the questions. What do we need to... Okay. What things do we need to change to make this work? How do we find what we need to change? And then there's the nitty-gritty of, you know, you have to make it work, you have to make it fast. How fast can you make it? How can you make it faster than that? You know, what's the peak performance? How much have you lost? What's the latency of the checkpoints? All that stuff. And so the plan is to do all of this work within GraalVM in the native image version, because the heap is something that is relatively easy to change in that implementation compared to some other VMs. Any questions before I conclude? This is the part where I list things you might work on. Yes?
Are you running this on actual hardware?
I haven't got any hardware yet. It just got released.
What are you using to simulate?
I'm not. This is a paper design. That's the whole point. It's not done. It's
What about the C, the extension to C?
the NVM Direct stuff is being run. There's both an NVM simulator that's available, but that's very slow. Also, you can sort of fake it by just mapping shared memory. And so the trick is you have a process that has a bunch of shared memory that it shares with another process, and then you simulate crashes by shooting the first one, and the second one, of course, doesn't go away. So it captures the current state, but it doesn't really do it doesn't test all of your flushes and your writebacks in the same way. And, you know, we have to actually know what those do first. Intel has to write some documentation for us to really be sure.
Is it inherent that non-volatile memory will always be slower than volatile memory?
That's not clear. Intel has got to the market sort of first. There are other non-volatile memory technologies, but they're in things that you wouldn't normally do CS research on, you know, small devices, embedded systems, things that needn't be fast, needn't be general. Intel has kind of brought this to market and got a lot of attention, but there are a lot of other companies working on underlying circuit technologies, and some of them claim that their underlying technology will perform as well as DRAM, if not better. So there's for example, there's a company called Nantaro that's building stuff based on carbon nanotubes, and they say it's going to be fast, but, you know, it's not there yet. And there are a lot of potential different technologies that are being investigated. So one of the challenges here is, if we make a bunch of architectural decisions on the assumption that DRAM will always be there, what do those decisions look like if DRAM goes away and we actually end up with everything being non-volatile? You know, over the very long term, kind of 10 years and beyond, there are even possibilities of cache hierarchies becoming non-volatile, because there are technologies that are very high read and write times, read and write speeds, but currently don't have endurance to be used in that situation. So maybe that will happen, but it's, you know, who has the crystal ball? Okay, so things that need to be looked at. And I've got two kinds of things. There's the short-term stuff, which is we have a bunch of stuff, we need to make it work. You know, existing languages, existing applications, practices, software, how do we get that stuff working in the non-volatile memory world? But there's a different question, which is, what's the best way to do it, really? If you started with a clean sheet, would you end up with the same thing as the first thing? Not really clear. So at the low level, there's a whole bunch of VM topics to look at. You know, once we're doing GC at terabyte scale and beyond, there are some real challenges in making that run as efficiently as you really need it to. You know, the current biggest machine you get with persistent memory is 24 terabytes, but I bet it won't be long before there's a petabyte machine out, you know, from some third party that does the interconnect and the engineering, because someone will want that, you know, right away. You know, NSA will order 6 of them, 10 of them, or something. You know, but is that the right way to do stuff as a single persistent heap and a GC of a large structure like that, or is there some other software engineering approach? Currently, we throw away compiled code. Very often, if we have all this memory that's really fast and big, maybe we shouldn't be throwing things away quite so often. How do you make the transactions, for some loose binding of that word, efficient in whatever your favorite language or runtime is? There's a whole bunch of work to be thought through there. And for the computer architect, where leveling in the DIMM is clearly suboptimal. It should be done centrally. You know, how much better can you do? Does it matter? Will anyone ever adopt your ideas? Who knows? Yes? Who knows? You know, it needs a viable production circuit technology. It needs the system level changes, a whole bunch of engineering. You know, I would imagine AMD is working on this. I have no idea what they, you know, if they are, what they're doing, but if this becomes popular, we're going to need other vendors to supply it, because one of the things is that, you know, enterprise customers generally get very nervous when there's only a single source for technology. It would be nice to have other sources and other competing models, at least for a while, but this is the only one that's really there at the moment. How do we build all the modular implementation independent stuff that we currently don't do? Right? How do we make the heap layout a portable thing? How do we back up live heaps as they're running? Does that have to be application level code written for every application? Can we do that in some way that's more general? Can it be piggybacked on the GC? How do we get old versions of things that we can recover to in the event of, say, a hardware failure and the loss of the data in the persistent memory? If self-relative data become really common, maybe there should be some addressing modes and instructions and some language support in unmanaged languages. NVM Direct has an approach, but can't be the only one. A big one is the dynamic software update issue and schema evolution. You know, there are all these languages out there that have to have this thought through. What happens if you don't have the source for the thing you're evolving? What if you have multiple versions co-resident? There's some really nice work, thought-provoking work from Gavin Bierman, who some of us know, on and James Noble on a system called Upgrade J, which makes versions an explicit thing in the programming language, which is an interesting direction to go in. Security, yeah, we need some. And that is all. So, last questions, yeah.
I make a suggestion that there's another category which sort of hinted at, it seems to me, which is basically usability.
Yes.
In other words, it's clearly possible to provide an API, but how can you provide
Yes. What are the best models? How are they used? What are the advantages of one model over another? That tends, you know, I suspect those things will be very specific to languages and communities and stuff like that, but that still needs, the work still needs to be done. Yeah. Or we just give them something and suck it up.
So, as you might know, there's a whole chain of software which has dealt with this problem for a while. Relational databases, SQL.
Yeah, so the world of systems that have already thought this through, it's just kind of get on with it. You know, they've in Oracle, they've figured out the language they want and the library they want, and they're just getting on with it. And that system already has a notion of transaction and consistency and checkpoint and recovery. And, you know, you throw a couple hundred people at the problem and you're done. It's not that difficult.
Well, I think that some relational concepts should be in general purpose programming languages.
That's another direction to go in. But there are so many different choices. That then gets back to the model. Which model do you want? How much sophistication are you assuming on the part of the programmer, or are you willing to make things less sophisticated but give something up like performance or scalability? And those things are really, you know.
It's might be kind of boilerplate inside. It's like VM code works in a private tenant. So like that's not very appealing for a lot of people to just get their stuff done. So you that much trade.
Well, I didn't know what level you want to put into the game trade. If we define tables, we define transactions, we define queries.
And there was a bunch of work done in the 80s and 90s trying to merge database concepts with programming language concepts, which is all kind of quietly being forgotten. You know.
Well, these went very far. Didn't get past the starting point. Yeah. Just, if it had fallen over backwards, would it have fallen back over the starting point? It was a commercial.
Keep sending the checks. Okay. Any final things? I think we're right on time. Okay, I'll be around till Friday morning, so if there's anything you want to discuss, I'm happy to discuss this further.